there are frequently times where integration by parts just one time isn't enough. Sometimes you get to do integration by parts more than one time. So here's an example where we have the opportunity to do integration by parts more than one time. So, perfect. Let's set up our integration by parts little table. So remember that we're taking the integrand and we're going to separate it into u and dv. So we have to break it apart. First off, when we look at this, I see two primary functions. I see x squared and natural log of x squared. It is very, very rare with integration by parts that you commingle functions. Like you might say, oh, well, couldn't we let u be x natural log of x and then let dv be x natural log of x? And yeah, you could. But that's very rare that would have any benefit. So when you're looking at this, we really have this polynomial x squared and then we have this log thing. So there's really only two choices. X squared as the u or x squared as the dv. And here's where my recommendation is to look at the dv first, because you want to put something in here that you can integrate. To get from dv to v, you're integrating. So we want to put the function in there that we know how to integrate. Do we know how to integrate natural log squared of x? No. We know how to differentiate it. We know how to use the power rule and the chain rule, and we can differentiate it. But we don't have a way to integrate natural log squared at this point. So that is the best candidate for dv. So that is the best candidate for u because we know how to differentiate it, but we don't know how to integrate it. So we'll put that with the u. And then with the dv, then we'll stick the other function. So we'll put the x squared there. So that makes the most sense because we don't know how to integrate natural log squared. We know how to integrate x squared. So then we build our little table. Derivative over here. Before I write it down, think in your head what the derivative of that is going to be. And then I will confirm that you are all thinking of the same thing. So, whoops. All these typing errors. So this is, the 2 comes down, the 1 subtracts, and then we differentiate. So we get that? Does everyone agree with that? So the power rule part brings the power down and subtracts 1. So that's 2 natural log to the 1. But then we have to differentiate the base, which is natural log of x. If you have to, not that this is bad, but if you want to, if this is helpful to you, you could write it like that. So the 2 comes down, you subtract 1 from the exponent, you get 2 natural log of x, and then the derivative of natural log of x is 1 over x.
Is there any reason, like, when you get farther in math, like, why they put the squared, like, in front of the x?
That?
Or, like, yeah.
They're just using that as a shortcut.
Oh.
I mean, it's just like trig functions, right? We write this all the time, sine squared, and what we really mean is sine of x quantity squared. So we do it with trig functions all the time. Most books don't do it like that with natural log, but some books do. So you just have to remember that it means 2's on the outside. Okay, what's the integral of x cubed, that thing? I think I heard it from someone. Charlie Brown. So now we do our uv minus integral of v du. So this is going to be equal to uv, that's the main diagonal, right down there. So uv, we're going to do a 1/3, we're going to do an x cubed, we're going to do a natural log squared. So there's uv minus the integral of v du. So we come right across the bottom. So uv minus the integral of v du. So here, my recommendation is to put everything inside the integral. It's very tempting to factor out your constants, which you can do, but in the long run, if you have to do integration by parts multiple times, pulling out the constants kind of makes it a little messier. So let's just leave the constants in. So we have 2, we have a 3 in the denominator. We have, how many x's are we left with? 2. We have an x squared, x cubed divided by x, so we have x squared, and then a natural log of x. And this is the stage where we do our assessment. And if arithmetic is hard for you, this might be hard. So we look at that integral, and if that integral is easier than the original integral, then we're probably going in the right direction. If it's not easier, then we probably chose incorrectly originally. And when we look at that integral, is there something noticeably better about it?
Natural log is not squared.
Natural log is not squared. So the power on the natural log function has gone down. So that's a good thing. So that means this integral is easier. Now we still have a product of functions. And remember that integration by parts at its core is a reverse product rule. It's when we have a product of functions that we primarily think of integration by parts.
Wouldn't you pull out the constant in front of the integral?
You can if you want, but usually what that means is, especially if we have to do integration by parts again, then you have to have the monster brackets, because that constant will have to distribute later anyway.
So you recommend us to just leave it in there?
For integration by parts, it's usually easier just to leave the constants in until the very end. So now we're going to use integration by parts again on this right there. So integration by parts again for that. And here, when we do integration by parts the second time, we want to make sure that we stick with the theme that we started the first time. So the theme that we started with is to put the natural log with u. If all of a sudden you switch your theme, you're just going to undo what you just did. And you're going to get back to the original problem. So if you were to switch and now put the log over here, then we would be undoing what we just did. So you want to stay consistent. So I'm going to put natural log of x with u, and I'm going to put 2/3 x squared over here for the dv. And then our derivative column will have du is 1 over x dx. And the integral column will be 2/9 x cubed. And so we're hoping that this is the last integration by parts. There are times where 2 is not enough. Hopefully it will be enough this time. Okay. Now we have to be very careful here because we have a leading minus. And we know with integration by parts, we are going to have a uv minus integral of v du. That's our ultraviolet voodoo. But if there is a leading minus, then this becomes that. We have to distribute the minus. If there's a minus out in front of all this, we have to distribute that minus. We just have to be aware of the minus signs when there's a leading minus. So we come over here, we do our uv, right down the main diagonal. So that's going to be 2/9 x cubed, natural log of x, and that minus, since this is positive, this now becomes negative with this leading minus. And now we have plus the integral of v du. So plus the integral of v du, and v du is 2/9 x squared. And that's easily integrable. So we're happy.
Easily?
Easily. Easily integrable. Power rule. Power rule. As easy as an integral can get, right? Integrating a power of x. Integrating a power of x is breakfast of champions, right? Integrating powers of x. All right, any questions on any of that step? Any of those steps?
What are the quotation marks doing there?
They're just saying that this comes down and this comes down. Yeah. So that, bless you. So those first two terms are just coming down.
If we forgot the plus C, will you be sad?
No, I'll be mad. Plus C. Red marker. All right. So this one is similar. We see a product of functions, so that, that kind of tells us that integration by parts is a good candidate when we see a product of functions. At its core, integration by parts is a reverse product rule. And once again, we have two choices. And what I want you to notice here is that up top, we put the power of x with the dv. As we integrated, that power went up, which in general seems like a counterintuitive thing to do because that seems like it's making it worse because the power is going up. But we had this offsetting thing of division by x over here from the derivative of natural log. So even though this power went up, when we multiplied those two, it actually just stayed the same. Right? We still ended up with an x squared. Down here, let's think about this for a moment. E to the x, or e to the 4x, an exponential, if you differentiate it or integrate it, it's still an exponential. And the exponent's not going to change. If you integrate e to the 4x, you get e to the 4x divided by 4, but the constant doesn't matter. The core, though, you integrate e to the 4x, and you still get an e to the 4x. If you differentiate e to the 4x, you still have an e to the 4x. So the e to the 4x, whether you choose to differentiate or integrate, it's just staying the same. Right? It's not getting harder or easier. But what about the x squared? The x squared, if you put it with the dv, it's going to be climbing if you integrate it. But if you differentiate it, it's going to be getting easier. Right? The powers are going to go down if you differentiate a power of x. So for this one, we actually want to do the reverse. We want to set it up this way because this side, the derivative column, is going to get noticeably simpler as we differentiate. The powers are going to go down. And the integration side doesn't matter. It's going to stay equally difficult. It's not going to get easier. It's not going to get harder. So it's not always as simple as saying, oh, put the powers of x here or there. It just kind of depends. One general rule of thumb is put the most complicated thing that you can integrate with the dv. And e to the x is more complicated than x squared. So that's another way to think of it that works. And over here, you can integrate natural log squared. So the biggest part, the most complicated part that you can integrate is just the x squared. Even though it's not a difficult integral, it's the biggest part that you can integrate. Okay, so then we have our ultraviolet voodoo. So uv, the main diagonal, we're going to have a quarter times x squared times e to the 4x. So there's our uv. uv minus the integral of v du. So minus integral v du. So that's the bottom row. So it looks like we have a 2 in the numerator, a 4 in the denominator, so we're going to end up with 1/2 x e to the 4x dx. And here's where we ask ourselves that question. Are we moving in the right direction? Yeah, power of x went down. That's good. If the power is going down, that's a good sign. All right, but we still have a product. And we can use integration by parts again. And we want to stick with our theme that we started with above. And that theme is to put the power of x with the u. So let's put 1/2 x right there. And we'll put e to the 4x dx right here. And then du will be 1/2 dx. And v will be e to the 4x over 4. And that should be enough to give us something integrable in our subsequent integral. Let's see. All right, so UV, main diagonal right there. So 1/8, and there's a minus, a leading minus. So we have minus 1/8 x e to the 4x. Minus the integral of v du, but remember we had this leading minus out in front, so it's actually going to become plus the integral of v du. So plus the integral of the bottom row, v du, and that is 1/8 e to the 4x. And once again, we see the integral and we say, oh gosh, that's easier, moving in the right direction.
So if the DUV was negative, like when you combine them, would that be plus 1/8 and then minus the integral of that?
Yes,
Okay.
exactly. So, oh, close. Which one did you say? If this one was negative?
Well, like the bottom one,
If this one was negative, then that would be positive and that would be negative. If this one was negative, this would be negative and that would be negative. Because the UV is what goes out here. So if we have UV and that's positive, then this minus will make it negative. The UV, that main diagonal. But both signs down here would affect the VDU. We'll see a few of them where the signs commingle. But the main thing is that if this is a leading minus right there, it becomes minus UV and plus VDU, integral of VDU. Okay, so then we have, pretty easy, these two terms come down. This is integrable. We have 1/32 e to the 4x plus c, or minus c, if you're a contrarian.
Why is that?
I wonder. All right, any questions?
What's next?
More integration by parts?
Oh, makes sense now.
It all makes sense now.
Oh no, natural log.
Natural log
Ew.
I hate that.
and a definite integral.
Yeah, we used to evaluate.
Ew.
Definite integral, integral, and a natural log. Okay, so once again, typically integration by parts, we are thinking reverse product rule, but we have these couple of anomalies, natural log, inverse trig functions. Integration by parts works really well for those two special cases, an inverse trig function or a log function. So when we come over here and we say, okay, let's do this with integration by parts, we don't have a choice because we look in here and we say, oh wait, integration by parts is a reverse product rule, but there is no product. There's only one function. Well, then that one function has to go with the u because we know how to differentiate it, but most of us don't have the antiderivative of log, even though we did it last time. That's not readily available for most of us. So then dv is just dx. And when we find our derivative in the derivative column, think about what that derivative will be, and then hopefully what I'm about to write down confirms what you are thinking. Everyone okay with that? Dustin?
Is it in a way to think of that still as natural log of 2 times x?
You should be thinking of it as natural log of 2x.
Okay.
So even though most of us don't write the parentheses here, that's how it should be.
Okay.
So if we wanted to write it as natural log of 2 times x, we would put the x in front.
Okay.
So we'd write it as xln2 instead.
Because ln of 2 is a constant, right?
Say again?
Ln of 2 is a constant.
So do you agree with that derivative?
Yes.
Does everybody agree with that derivative? Joseph? Do you agree with it?
Ish.
Yeah, exactly what I was suspicious of. Chain rule?
Yeah, where's the two?
What happened to the twos?
Yeah, where's the two, bro?
What did they do? They annihilated each other. Kaboom. Right? If you have y equals natural log of 2x, the derivative is 1 over 2x times 2. Do we eliminate the issues?
What? Yes, twos are gone.
Okay, so then we have our u times v, that's the main diagonal. And keep in mind that this is a definite integral. So if it's a definite integral, we're going to have to put these limits of integration on both the uv and the integral of v to u. So there's the uv with the limits of integration. uv minus integral of v du. Oh, what's v du?
1.
Yeah, x and 1 over x, they cancel. We have that. X times 1 over x is 1. Now you can evaluate this the uv part on the 1 to e thing. I find it simpler just to wait, since you're going to integrate this over here and still evaluate from 1 to e. Why not just do all the evaluation all at once? So we can do that. You can evaluate on the front and then do the integral and then evaluate on the right, when you're done. But you're evaluating between 1 and e. Why not do it all at once is my strategy. So we have that. Now we'll do our evaluation. We plug in the e first. So we're going to have e natural log of 2e minus e. Now we subtract off antiderivative evaluated at 1. So we're going to subtract off, plugging in a 1 for all these x's. We're going to have 1 natural log of 2. So minus natural log of 2, and then plus 1.
Plus 1.
Plus 1. Subtracting off the antiderivative at 1. There's a little bit of simplification that can happen here. What can we do with that 2e? Anyone have a log property or something you can do?
Split it
into,
ln2 and ln e.
so if we have something like
It'd be plus.
natural log of 2 plus natural log of e, isn't that the same thing as natural log of 2e? Right, so that's the product rule for logs. Everyone agree with that? And then what's natural log of e? 1. So we could do this. So we could say, oh, let's make this natural log of 2 plus natural log of e. Natural log of e is 1. So this will be e natural log of 2. That we just said is 1, so we're going to get a plus e minus natural log of 2 plus 1. So we'll get a little bit of simplification. So the e's cancel, and that's about it. So notice here that we put the e in front of the natural log of 2 to clarify that 2 is that the piece inside the natural log is just the 2. So usually, as we're writing things out, we'll usually put logs last so that something doesn't, it's not supposed to be in the log. It doesn't look like it's in the log. Okay, here's another one. Definite integral. We certainly have a product here. We have the function y, and we have the function arctangent of y squared. So we have a product of two functions. We don't know how to integrate inverse tangent. Inverse trig functions, we know how to differentiate, but we do not know their antiderivatives. We do not know the antiderivative of arctangent. We know its derivative, but not its integral. So that means it's going to go with u. So now you all differentiate this correctly, please. So differentiate that. Oh, what am I doing here? That's a dv, and this is a dy. Yeah, it gets confusing when they switch it to y all of a sudden. So differentiate that. And you differentiate it. So the basic derivative is 1 over 1 plus x squared if you're looking at an arctan of x. So basic arctan derivative. One over 1 plus x squared. All right, let's see if you did it right. So this is going to be 1 over 1 plus y to the 4th. And what goes in the numerator? Say again?
2y.
2y. 2y. 2y goes in the numerator. Everyone agree with that? So the derivative of the inside of the arctangent is 2y. That goes in the numerator. So that's our chain rule piece. So if you take that derivative wrong, you are just going to get into a world of hurt. So again, very, very important to have your basic derivatives with chain rule dialed. So UV, main diagonal. So we'll put this stuff out in front of the arctangent so that it doesn't accidentally look like there's more inside the arctangent than there is. But most of us don't put parentheses around this, even though that would be smarter and better. Most of us don't do it, though. It gets too tedious to write parentheses everywhere. So UV, and now the limits of integration here are 1 to 1 over root 2. Minus the integral of v du. So minus the integral v du, we get y cubed over 1 plus y to the 4th dy. And these limits are 0 to 1 over root 2. Everyone see the v times du? There's a 2 in the numerator, a 2 in the denominator, so those cancel. And then y squared times y is y cubed.
That's doable.
So it's v du. What's that?
Can we multiply that by 4?
So this is in log form, almost-ish. It'll be in log form in one moment when we use our creative 1 to multiply by 1. Now it's in log form. If you didn't get this derivative right here, you would be stuck there. You wouldn't be able to integrate. But because we didn't make that mistake, we have a log form integral. Question?
In the du, how is it y to the 4th?
Right here.
Yeah.
Because the rule for an arctan is that we do 1 over 1 plus the inside squared. So whatever's inside here gets squared.
Oh.
And the part that's inside over here is a y squared. So when that gets squared, it becomes a y to the 4th. You see it?
Yeah.
All right, so you could evaluate this UV piece right here, but I say just wait. So we're going to have 1/2 y squared, arctangent y squared. Now we can integrate. This is minus 1/4, natural log 1 plus y to the 4th. We don't need an absolute value because that thing is never negative. y to the fourth is always positive. And then this will go from 0 to 1 divided by square root of 2. Yeah?
Could you explain to me again how
Mhm.
how do you make that into, like, by pulling a fourth and a front and a 4 made into log function?
Yeah.
Log form?
Yep. So remember that log form looks like this. So log form is when we have this situation. This will always be natural log absolute f plus c. So the denominator's derivative is identically the numerator. So when we look at that y to the fourth, its derivative is 4y cubed. So in order for this to be in log form, we need that numerator to be exactly the derivative down here. The derivative down here is 4y cubed. So we know we have to multiply by 4 to match, so that that numerator matches the derivative. But if you multiply by 4, you also have to divide by 4. That make sense?
Yep.
And then we can evaluate this whole thing all at once. Let's just notice that when we plug in 0, we get 0. If you plug in 0 here, you get 0 squared, which is 0. Multiplied by anything is 0. Natural log of 1 plus 0 is natural log of 1. Natural log of 1 is 0. So this is not going to contribute anything. So we can focus our attention on that upper limit of integration. So plugging in 1 divided by square root of 2. When we plug in 1 divided by square root of 2, right here, that becomes 1/2 times 1/2 is a fourth. Times arctangent of 1/2. 1 over root 2 times 1 over root 2 is 1/2. Minus a quarter times natural log. Okay, 1 over root 2 4 times is a half times a half, which is a fourth. Plus 1, 1 plus a fourth is 5/4. So that's what we have. One over root 2 multiplied by itself 4 times is 4. So we have 1/4. 1/4 plus 1 is 5/4. And that is as far as we can go, because we don't know an angle that has a tangent value of 1/2. We know an angle that has a sine value of 1/2. We know an angle that has a cosine value of 1/2. But we do not know an angle that has a tangent value of 1/2. So we can't simplify that.
What if you put 1/2 into a tangent function? Will it produce undefined or something?
No, you can get there. It's just an irrational number.
No.
So it would be an irrational angle, an irrational number of radians. So the only special values we have for tangent, we know arctan of 1. The angle that has a tangent of 1 is which angle? 45 degrees, pi over 4 radians. We know the angle that has a tangent value of root 3. Which angle has a tangent value of root 3? 60 degrees. Oh, circle. So if you're looking at on the 12 sector unit circle, so the clock, this one has a slope of root 3, m for slope right there. That, and tangent is slope, right? Tangent is slope when you're talking about terminal rays, y divided by x. And this one, where the point is root 3 over 2 comma 1/2, this one has a slope of root 3 over 3. So those are the three we know. Arctan of 1 we know, arctan of root 3 we know, and arctan of root 3 over 3. Those are the only three we know for arctans. If it's any number other than 1, root 3 or root 3 over 3, we can't do anything. It's just an irrational angle. All right, any other steps there? Questions on evaluating? right, so arctangent. All right, let's do solid revolution. We've got one bump of sine. No, we shouldn't use that word. We've got one lobe of sine. Let's not talk about bumps. And then we have a rotation around the y-axis. All right, there's only one natural integration technique to use here. Shell, washer, or disk? No.
Shell.
No.
Gel.
Excellent. Excellent. Bonus points. He didn't strike out. When there's only 3 answers, you can't strike out. Let's do multiple choice with A, B, and C. Okay. Why does it not make sense? So let's understand why. If we were going to use a horizontal element, that would be the washer. Disk is not even in the conversation because there's a gap right there, right? So disks is not an option. But we don't want to use a washer because this is sine x here and that's sine, right? Both sides are sine. That's a problem. You can't have the same function be bounding the element on both sides. So that's why washers don't make sense. So we're going to use a shell. We're going to use a shell. And we know that the area of a cylinder, the area of a shell or a cylinder, is 2 pi RH. The radius is the distance from the axis of rotation over to this random element that we're putting at a random x. There is the radius of the cylinder that's going to be created by rotating that element around the y-axis. The height is the height of the element. There's the height. So there is our cylinder. Are we going to be integrating with a dx or a dy?
dx.
Dx. Vertical element, the thickness is dx. So we're integrating with dx. So that's just a check. Before you start plugging stuff in for R and H, if you have that in your mind that you have a vertical element, that tells you dx. Horizontal element tells you dy. That just confirms, it reassures you that you know that you should be, everything that goes in here should be x's. So what is the radius going to be?
X.
X. And what is the height going to be?
Sine x.
Sine x, yeah, perfect. So that is the area of the cylinder at x. So for every x, you should be envisioning this big sort of nested cylinders. Everywhere you draw a vertical element, it rotates around the x-axis or the y-axis, creating a cylinder. So you should just see a big bunch of nested cylinders. So volume is the integral of area. So we're going to integrate this product from 0 to pi. So that will give us our volume. Ultraviolet voodoo, we have a product. We're going to use some voodoo. So here is another scenario. We've got 2 functions. We've got the x function. We've got the sine x function. Let's think about sine for a moment. If you differentiate sine, you get cosine. If you integrate sine, you get cosine. Maybe there's some pluses and minus ones. Doesn't matter. But the essence, if you take sine and you differentiate or integrate, you get cosine, which is about the same level of difficulty. But x, if you differentiate x, you get 1. If you integrate x, you get x squared over 2. So that gives us a clue that we want to put the x here because that column will simplify things. Right? If we put the x in the derivative column, it gets simpler when you differentiate. The sine, regardless of where you put it, is going to create something about the same difficulty. So this is good news. This will work. So we have 2 pi times. So here's an example where we factored out the constant, and now I'm kicking myself because now I have to use monster brackets. It would have been easier just to leave it in there, but now we have to put in these monster brackets. So 2 pi times this integration by parts, we have u times v ultraviolet, so minus x cosine x. There's our uv, ultraviolet. That has to be evaluated from 0 to pi. Minus the integral. All right, now we can think about your question, Alex. So what should that sign in front of the integral become?
Positive.
Positive, because so we did the uv, that's negative, but then v du is negative. So that negative on the inside comes out here and makes that positive. And we have that going from 0 to pi, close the monster brackets. You can see why just leaving the 2 pi on the inside would have made our lives a little bit simpler. We wouldn't have to have these monster brackets. So again, we'll do the evaluation all at once. The uv has to be evaluated on the interval 0 to pi. And then whatever the integral of this is has to be evaluated 0 to pi. So let's just wait, do it all at once. And right away we notice that 0 is not doing much. Plugging in 0, both terms become 0. Sine of 0 is 0. 0 times anything is 0. So 0 we can kind of ignore.
What about pi?
Yeah, what about it? So we can't ignore that one. What is cosine of pi?
-1.
Negative 1, thank you. And then what is sine of pi? That one is 0. So when all is said and done, we get 2 pi squared. 2 pi squared. So that will be the volume of the solid of revolution.
9.8 times 2 is 19.6.
We don't care about approximations. This is math.
Pi squared is gravity.
So any questions on any of the setup there? Hopefully cylindrical shells are feeling
Doable.
manageable. Let's use the word manageable. Let's go ahead and take our 10-minute break, right? Did we start at 3? Has it been a whole hour already?
Yeah.
Right? Time is flying. You guys are blessed. Oh. Okay, so let's go ahead and look at a couple more of these. So we now get to do ultraviolet voodoo with a twist. With a twist. So we've had ultraviolet voodoo, we had repeated ultraviolet voodoo, and now we're going to have ultraviolet voodoo with a twist.
Trace it.
We're just going to get easier.
All right. So first thing is that we need to call this integral something. So we're going to pick. We could call it S, if you want to use S, or V. You could use whatever letter you want. You could call it Steve, whatever you want. I'm going to use a single letter. Usually the textbooks use a big I, but that's kind of boring. So we're going to use that symbol, omega. If you want to use, you could use ohm, you could use gamma, you could use
Lambda.
lambda.
My question is, so, I mean, you probably already know it because, you know,
Oh yeah, I've done this before.
you've done it multiple times.
Yes, yes,
But
yes. yes.
how can you tell automatically when that's going to have that twist? When you look at the
We're
problem.
gonna we'll talk about why it's going to be twisted in a minute. Yeah, we will twist one. So we are going to know that it's going to be twisty because of the following. When we go to do our integration by parts, here is what we're going to notice. So think about e to the x and think about sine of x. Forget about the coefficients for a minute. So both of those functions, regardless of where you put them, are going to repeatedly kind of be similar. If you put the sine function in the derivative column or the integral column, if you differentiate or integrate, you're going to get a cosine. So it's going to stay equal difficulty. So it's just going to cycle, right? If you put a sine with u or a sine with dv, it just becomes the other function, it becomes a cosine. But doesn't that also happen with e to the x or e to the minus 2x? Doesn't matter. If you have an exponential and you differentiate, you get another exponential. If you have an exponential and you integrate, you get another exponential. So that's how you know that it's going to be a twist. If both functions cycle. Like when we had this last one right here, both functions aren't cycling. Here, sine is cycling whether you put it with the derivative or the integral. But here, x is going down in power. So if you have two functions that are going to do that cycling thing, that's when you're going to get this twist. So if we look at the prior one here, up here, not that one. If we look at this one, no, that wasn't it either. I don't know. Yeah, if both of them are going to be cycling, that's when you get the twist. So with most of them, one of them can be sort of cycling, but the other one is going down in power, then you're not going to get the twist. All right, so here, it's not going to matter. Exponential and sine, both are going to sort of cycle, so you can pick whatever one you want to go with whichever one, and it's going to be fine.
When you say cycling, you mean like we're gonna have to do the ultraviolet voodoo multiple times?
We're going to have to do ultraviolet voodoo with a twist
Okay.
when both are cycling. So like if like that one that we did on the back board there, when we took the derivative of x, the power went down. The sine part is cycling, but the other part is getting simpler.
Okay,
So-
cycling in the sense that it's just like, is this gonna be specific to trig?
Yes.
Okay.
And it's going to be specific to having an exponential and a trig function usually. So that's kind of the telltale sign that we have a sine or a cosine and an e to the x, that it's going to work. Dustin?
If you look at the -2 and the 3x, and we'll try to simplify one of those, like you ignore the e and the sine.
Well, these coefficients aren't going to change the nature of it.
Okay.
So like down here, I'll have you guys do this one that has no coefficients.
Yeah.
And it's just simpler with no coefficients. The coefficients won't change the nature of it. It'll change the details.
I was just like thinking if you look at that maybe to make one simpler or something. But it
And we're not going to be able to make the angle or the exponent here simpler because the derivative of e to the negative 2x still has an e to the negative 2x.
Yeah, you're right.
And the cosine, the derivative of sine 3x, we still have a 3x in the angle.
Everything comes in.
Everything comes with the derivative or the integral. So here, let's go ahead, we'll go through this one, and we'll see what I mean by twist. So the derivative here looks like that. The integral here, integral of sine is minus cosine. And then we have to do the reverse chain rule. Okay, so what we notice when we do our, let's do our uv minus v du. So I'm going to call this whole integral omega. You can call it whatever you want. I'm just going to call it omega because we're going to have this interesting twist that's going to happen. So uv is minus 1/3 e to the minus 2x cosine 3x. So that's the main diagonal, u times v, ultraviolet, right there. uv minus the integral of v du. So minus the integral of v du. v du is positive. Both v and du are negatives. So when you multiply these two together, you get a positive. So this minus out in front is just going to stick around. So we're going to have 2/3 e to the minus 2x cosine 3x dx. Dan?
Since this is an indefinite integral, is it okay to pull the constant out, or do we still want to leave that in?
I would still leave it in because we're not done yet.
Okay.
So we can pull it, as soon as we have an integral over here that's integrable, then you could pull it out. But right now we're still dealing with a product, which means more integration by parts, which means it's probably better to leave the constant on the inside. So as soon as you get past the integration by parts, then you can pull it out.
Thank you.
So now here's where we do our assessment. We look at that integral and we say, oh, is it easier? Or is it harder? Or is it the same? And it looks about the same as the original one. Okay, we have a 2/3, but that's just a constant. We could think of it as factored out. The essence of this integral, though, is exponential times trig function. That's the same as this. So if it didn't get worse, you're on the right track. If it didn't get worse, you're on the right track. And it did not get worse. The power here didn't all of a sudden get bigger. The angle here didn't do anything mysterious. Still has kind of the same feel. So we're going to do integration by parts again. And we will see the twist very soon. Now, one of the things that you really need to keep in mind is that we want to stay with the same theme. If we chose the exponential for u, we want to choose the exponential for u. If you reverse your theme, you're just going to undo what you just did.
Wait,
So
what is the twist again? Have we got
we're going to get to the twist. Oh, you'll know the twist.
Okay.
You'll know. You'll know it when you see it.
Is it 0?
No. No. The twist is not 0. So we're going to stick with the exponential for u, and we're going to stick with the trig function for dv. So there's the udv. So udv, we parse our integrand into two functions, two pieces, u, dv. The derivative on the left, we're going to get minus 4/3 e to the minus 2x dx. Chain rule derivative. Derivative of an exponential is itself multiplied by the derivative of the exponent. Integrate here. Integral of cosine is sine, but reverse chain rule, RCR. Divide by the derivative of the angle. Okay, so we've got our omega over here, left side. We'll just rewrite this. We could put a little quotes here instead of rewriting it. Doesn't matter. I have two C's. Okay, so now we have a leading minus. So we've got to be careful with signs. So leading minus. So UV, that's positive, but we have the leading minus, so that makes it minus. So minus 2/9 e to the negative 2x sine 3x. Okay, so there's UV minus the integral of v du, but we have that leading minus, so it's going to be plus the integral of v du. But v du is negative, so that will be negative. So we'll talk about those signs again in a minute. 4/9 e to the negative 2x times sine of 3x dx.
Isn't it positive?
No.
Back to that.
So let's talk about how many minuses there are. So we have, so remember that if we have uv minus integral of v du.
Never mind.
Do you see it?
I do.
So we have this leading minus out in front. There's one minus. And then we have this minus right in front of this integral. There's two minuses. And then we go to v du, and there's a third minus. So we have three minuses, so we're going to end up with a minus in front. There's a few ways you can think about it. If you have a leading minus in front of all this business, this is going to be minus uv plus the integral of v du. And if you have plus the integral of v du, whatever the sign on v du is, that's what's going to persist. So we have plus the integral of v du, but v du is minus, so that sign is going to persist. If you have plus the integral of v du, and v du happens to be negative, then you're going to end up with a minus in front. So a couple ways you can think of it, or you can think of 3 minuses as a minus. Now here, notice this fact. This original form, e to the minus 2x sine of 3x, isn't that what we have right here? So this, we aren't twisting yet, but we're about to twist.
Getting ready.
We're getting ready to twist. This is 4/9 omega. Everyone agree? Minus 4/9 omega. Omega is the integral of e to the minus 2x sine 3x. So we have minus, so here we can pull out the minus 4/9 now. Pull out that constant, and then we're left with omega. We are left with the original integral. And here's where we twist. What do we do? Now we're back to algebra 1. If you have some omega on the right and you have some omega on the left,
Cancel it.
you twist them over and combine them. Right? We combine the like terms. On the left, we could write this as 9/9 omega. So we have some omega there, we have some omega there. Put them together. How many omega will we have on the left? 13/9.
Yeah.
So then we still have this. We'll fill it in a minute. We still have this. And now one thing that we have to remember is that our original integral is indefinite. We know the very end with an indefinite integral, we have a constant of integration. So we have to remember that as soon as we do this interesting twist where that comes over to the left, we want to make sure that we don't forget our integration constant. So that's where we're going to put our integration constant.
Wait, okay.
Yep,
Where'd the 9/9 come from? Oh, that's just one.
that's just one.
And you're just doing that so that they're common denominators.
I appreciate it.
What she said. We want a common denominator. So we're going to rewrite omega as 9/9 omega so that we can combine them. What's
That's
it? That's it, man.
That's it.
Almost. One more step. What's the last step?
So multiply the other side by 9/13.
Bingo!
That's what I did.
What he said. So the last step is to isolate omega, so we multiply by 9/13. Because the question said we want to solve for omega. We don't want to solve for 13/9 omega. We want to solve for omega. So the last step is to multiply both sides by 9/13. So we're going to multiply by 9/13. We're going to multiply by 9/13. And when we multiply c by 9/13, that's still just a constant, so we'll just write it as c. It is a different constant, but it's still just a constant. We don't have to be finicky. We can just write it as c. So now we have solved for omega, or Steve, whatever you want to call the original integral.
So does the omega include the integral, or is it just what's inside the integral?
It is the integral, so it includes it. So this omega is the whole thing here. So omega is the integral of this product. And so down here, the integral of the product, we can factor the constant out, and it's going to be -4/9 times the integral of the product. So there's where we pull it out, once we're sort of done with the integration by parts.
So in order to do the twist, you have to do it at least twice.
Yeah, so integration by parts with a twist.
Because
This way?
you have to get back around to the original.
Exactly. So you're going to have to do integration by parts twice to get back to where the integrals match. So if you have an e to the x and a sine of x, you go twice, so the sine goes to cosine, then back to sine, and the e to the x stays e to the x each time.
Okay, I was deep in the writing sauce. So where's the twist?
The twist is when we take this and we twist it over to the other side.
Okay, so. Is that's how it
Anticlimactic, huh?
became- Yeah, so that's how it became 13/9. Did you just add?
I added 4 plus 9. So if we add 4/9 to 9/9, we get 13/9.
Okay.
And then to get rid of the coefficient in front, we're going to multiply by the reciprocal, so we multiply both sides by 9/13.
Okay, so you know that it's time for the twist when you've got omega on the other side, and it's time to go.
It's time to go, man. We have omega. We have omega on both sides. It's time to go. Right? You always have to have some sort of clue so you know when it's time to leave. So, yeah, as soon as we have omega in both places, time to go.
So would you
Let's
say,
go.
if this was a test question, would you say there may or may not be a twist?
Yeah,
Okay,
I give you some sort of hint.
thank you.
I'll give you some sort of hint.
Because I'll end up going, through the entire page.
Right. You keep going again and again and again and again.
I would do that.
All right, you all try this one. Try that one. So I took out all the coefficients. So this has the least distractions possible. There's no coefficient in front of x. There's no coefficient in front of x in either place. All right, let's see if you can do it.
This one's nice.
This one's nice.
This one's really nice.
Yes, exactly.
I like this.
Yeah.
Lots going on.
Just a nice x.
You are the solution.
So you are, that's nice.
You are the solution.
Depends on the question, I guess. Like really natural one. Yeah, engineering question. Y equals 3x plus 2.
Exactamente.
I'm linear.
You're non-linear? Yeah.
Because everybody gets I don't like this negative sign.
You have your own formula.
You should have put it with the other function then.
I'm just gonna bracket it.
Bracket it. So if you are better at differentiating the trig function than integrating, then stick the trig function with the u. If you're better with derivatives. If you're terrible at both, then it just doesn't matter. Just put it wherever. Just try. Try hard, but don't be a tryhard. If you're on the highway and you see James, slow down. Yeah. This sounds scary, man. Right? Yeah. I know, it psychs you out. So what it is doing is simplifying. It's simplifying the integral. So here we have the integral of the product. But when we do our ultraviolet voodoo, we have the integral of just a single function. So that's the nature of ultraviolet voodoo, is that it takes a product and it's simplified. When we don't know the antiderivative for x sine x, we don't know the antiderivative. So what it does is simplify the integral piece to just the integral of one function that we can. So that's what we're trying to do here. We've got this product. Product, two functions multiplied together.
So this would be negative 2 of x.
Correct.
Position of the product.
That's right.
And then this is just let u be that.
Mhm.
And then d is, why is this one not just b?
So we start out, so with ultraviolet voodoo, we are taking
So that means what?
right there. So we are taking UdV, so we're taking the integrand over here, and we're separating it to U and dV. So that's what this is. We're taking the integrand, and we're separating it to U and dV.
So dv is the derivative.
Yes.
Why, how
And we have to integrate to get to v. So we have to differentiate u to get to du, and we have to integrate dv to get to v.
So why is this the derivative?
So that's just how integration by parts works. We separate, a piece of it is going to be u, and a piece of it is going to be v. Yes.
And then we integrate that piece,
To get to v,
and we take the derivative
derivative
of
of that
u.
piece to get to vu.
Why do we do, so this is obviously what it's doing.
Yeah.
But why do we do the derivative?
Derivative, so UB, the integral, let's see, UGB, integral of UDB. is going to be uv minus integral v. So we have to have both v and du in order to fill in
It's
these.
just based on this, really.
Yes.
The integral of this is equal, it's two integrated parts. Minus the integral of its derivative.
So that one doesn't have a derivative. We have to get to v, so v du.
No, it's, I mean, if I have a plus.
I don't even understand how this mathematically makes sense, but as long as I know the steps. I'll take it.
Yeah, the steps are key. All right, you all get it?
I wanted you to confirm it.
I am going to confirm. Do I see a plus c in there?
No.
Or are you writing just in faint pencil that I can't see? All right, let's try it. So it's not going to matter. You can choose your own adventure.
In conclusion, add your C and forget that.
So you can choose your own adventure. You can put the cosine with u or the cosine with dv. Doesn't matter. All right, so it's not going to matter. So du will be e to the x dx. V will be sine of x. So we are going to call this integral omega, or whatever your favorite letter is. So omega will equal uv minus the integral of v du. Isn't it amazing how much easier it is without a bunch of coefficients?
Yeah.
Dx. So when we look at that new integral, it's the same in difficulty as the original. We have an exponential, we have a trig function. So it hasn't gotten worse. If it hasn't gotten worse, persist. Keep on going. So now we're going to use integration by parts again and use the same theme. So there's the breakup of the integrand. So u dv. And then we differentiate the left. We integrate the right. So uv. Now here, uv is negative, and we've got this leading negative, so this is going to make us have a plus e to the x cosine x. So there's uv minus the integral of v du. So we're dealing with this. So we had a leading minus, there's one minus, there's a second minus, that makes us a plus integral of v du. V du happens to be negative, so we stick with the negative. So minus integral.
I'm sorry. Cosine's negative. Cosine's negative.
So one negative,
Yeah. Two negatives.
two negatives, three negatives. Make a negative. Right there, negative.
Yeah. But I think
So that's going to make it plus the integral of v du.
right.
And v du happens to be negative, so a
Oh.
positive times a negative is a negative. That's the hardest part, figuring out whether the sign is positive or
Can I
negative.
just take the absolute value of it?
So that is what we decided to call omega. So that's an omega over there. So now we have omega equals that plus that minus omega. You see it?
There we go. Two.
You can use that one. Whatever letter, your favorite letter. You can use a Devanagari letter or character.
I've never heard of it.
Use a da. Okay, so twist. When you have two omegas, twist them together. How many omegas are on the left? Two omegas. Plus c. As soon as you twist your omegas, make sure you put a plus c. And then we divide by 2. Excellent. Integration by parts with a twist.
Is it finite factor?
All them brackets.
What's that?
Is it okay a factor?
No. Yeah, I mean, you don't want to factor because you can't factor out of everything. Right? Because you have the c.
I couldn't factor an exponential out of that.
But you can only factor it out of the first two parts. You can, but there's not any added value. Usually if we factor, we want to factor out of everything.
It made it easier.
Maybe.
I have to write a negative for one half.
Oh, yeah.
You can do that. You can do that. Dan?
I was just confused about the taking out a common factor from C. Can't we multiply or divide C by any number and it's still just another constant?
Yes. But we can't factor out a function exactly. Like we can't factor out e to the x from it.
So we can take out 1/2 but not any.
Yeah, exactly. Yeah. So usually if you're going to do some sort of factoring as a final answer, you want to factor it out of everything. Like if you're ending up with an answer like x squared plus x plus 1, you wouldn't write it like this. Right? Like it doesn't help us to factor just out a part. Usually if you're going to try to do a factor, you want to factor it out of everything so you can figure out what the zeros are. Right? We never factor out of just the first two terms and not out of the third. Most of us. Dustin?
So you did it how I did it, and I got the same exact answer. But if you did it the other way, you'd still get the same exact answer?
Yes. If you did these swapped,
Yeah.
you'll get the exact same answer. Yeah. They will look identical.
Is your T not divided by 2? Or C?
You can treat the C like it's a recycle bin. And if any constants get added to it or multiplied to it, you just call it C. Still a constant.
What if I just had the expression all over 2? Is that okay?
Yeah, that would work too.
But you can.
Okay, so let's get out of here.
Really?
Oh, that was from the other.
Yeah. Let's get out of A2. Time for A3. Okay, so this stuff in 8.3 is not hard, but if you don't pay attention, it will feel hard. So we are going to be dealing with powers of sine and cosine multiplied together. And we're going to be dealing with powers of secant and tangent multiplied together. And we're going to have a couple of strategies to integrate powers of products here. So here is the sines and cosines are easier. Why? Because the derivative of sine is cosine. The derivative of cosine is minus sine. The tangents and secants are more complicated because the derivative of tangent is secant squared. Derivative of secant is secant tangent. They're just more complicated derivatives. Sine and cosine, the derivatives are essentially each other, so it's a little simpler. So here is the rule. We already know that if we have an even power on sine or cosine, we do power reduction. Right? We did that last time. Power reduce. So here is the new thing. If one of the powers is odd, we're going to split off a factor for the differential and convert the leftovers. So here is what that means. So here we see an odd power on sine, so we're going to pull off a sine. And that's going to leave us with sine squared. These are leftovers. Right? We pulled off a sine, we left the sine squared behind, those are leftovers. We are going to convert the leftovers to the cofunction. So we're going to convert the sines to cosines. Why? Well, if we pull off this sine and stick it with the differential, we're doing that with the understanding that if we let u be cosine, then that would be its derivative. Right? And that's how u substitution works. For it to work, the derivative of u needs to be available. So if we let u be cosine, the derivative is available right there. So if we pull sine over to the differential, we want to turn everything else into cosine so that we can let u be cosine, and then the derivative will be the differential. So let's try it. So we convert the leftovers. We let u be cosine. du is minus sine x dx. And if you want to, you move the minus over. If you want it to match exactly, because that's how you are. So now it matches exactly. So we're going to replace that part with minus du. And then here, 1 minus u squared. And we end up with a pretty easy polynomial to integrate. Powers of u. So we're going to end up with minus u when we integrate, and plus u cubed over 3, plus c, and then we back substitute. So that's our strategy. Odd power, pull one off and convert the leftovers. That's our strategy. Powers of sines and cosines. Pull one off, convert the leftovers.
Power rule still gives us locally.
What was that?
Power and rule still gives us if we reduce derivative.
Louder.
Sine, integrate.
Yeah.
Never mind.
Yes. 100%. Okay, so when we look at this power on cosine, we see an odd. Sine we can't do anything with, so let's leave that. But if we have an odd power on cosine, we're going to pull off one of them, and we're going to convert the leftovers. So we're going to put the cosine with the differential over there. So that's just in a holding pattern with the differential. And we're thinking ahead. We're saying, oh, the derivative of sine is cosine, so we want to turn everything else into sine. Right? If all this stuff over here is sine, we'll let u be sine, and there's the derivative of sine. So we want to convert the leftovers so that we can then let u be sine. All right, so converting the leftovers, we've got sine squared. That's just sticking around. We're going to let u be sine, so that's already positioned. Cosine squared is 1 minus sine squared. So cosine squared is 1 minus sine squared. But then we have to square it to get to the fourth power. So now we've converted the leftovers. Now we can let u be sine, and du is right there. That's all lined up perfectly for u sub. So if we let u be sine, du is cosine x dx. Any questions before we evaluate that? Yep.
What was the rule for this one again?
If you have an odd power, pull one off and convert the leftovers. If you have an odd power on sine or cosine, pull one off, convert what's left. Convert, backfill. So let's go ahead and do our u sub. You could multiply this all out ahead of time, but it's going to be a little easier to multiply this out when we just have u's. Any issues with that?
So is it going to be
Issue free?
No, yeah.
All right, so then foil. You know how to foil? And then distribute that u squared. We've got that. And the nice thing about these is that they really, this procedure always leaves us with something very easy to integrate. And then last step, back substitute. We got to get rid of the u's, got to get back to x. And we said that u was sine of x, so all we do is replace the u with sine x. 1/7. Let's see. So both powers are even on sine and cosine. You've got to do that power reduction thing. But if one of the powers is odd, then we can do this. All right, any question on sine and cosine? So the main idea is that you pull something off so that you let u be the function that has what you pulled off as the derivative. So if you put cosine off to the differential, you're going to let u be sine. If you put sine off with the differential, you're going to let u be cosine. So now with and it's a little more kind of transparent with sines and cosines. Tangents and secants are a little bit more complicated. And the rule changes based on the powers. So with sine and cosine, all you're looking for is odd. That's easy, right? Here it's a little different. So if the power on secant is even, we're going to pull off secant squared. All right, so let's think about this. So the derivative of tangent is secant squared. So if we're going to pull off secant squared, we want to let u be tangent, because the derivative of tangent is the secant squared that we pulled off. So let's think about this. Secant has to have an even power, because if we pull off secant squared, then it will still have an even power. And you can convert secant squared or secant to an even power to tangents with the Pythagorean identity. Right? All those Pythagorean identities have squares. And we know that we can convert using the Pythagorean identity. We know that tan squared of x plus 1 is secant squared. So if we pull off secant squared and we're left with an even power of secant still, we can convert those to tangents really easily. All right, so if we pull off secant squared, we need to have tangents over here. So let's see what happens. All right, so, even power of secant. Let's pull it off. All right, now this one is, I'm just going to rewrite it so that I'm thinking in my head that I've pulled off the secant squared. It's hanging out with the differential. There's no leftovers. We pulled off secant squared. There's only a secant squared. So we can just go straight to let u be tangent. So we can just cut right to the chase. U is tangent. Du is secant squared. So this integral is nothing more than u squared du. So we'll integrate. We'll get a third u cubed plus c. We'll back substitute. And that'll be our final answer. Okay, so secant to an even power, we're going to pull off secant squared. If tangent is to an odd power, we're going to pull off a sectan. So let's think about this. So if we know that the derivative of secant is sectan. So if we're going to stick a secant over with the derivative, over with the differential, what do we want to let u be? Secant. Right? We want to let u be secant because then its derivative will be secant tangent. So we're going to have a secant tangent over with the dx. We're going to let u be secant. Notice this, that if tangent is to an odd power and we pull off a sectan, we're only pulling off one tangent from an odd power, so then we're going to be left with an even power on tangent, which can be converted using a Pythagorean theorem. All right, so all of our conversions, when we're converting leftovers, they have to be to an even power, so you can use the Pythagorean theorem to convert them. So let's look here. Okay, odd power on tangent. The rule says pull off a secant. There's no secant. So what do? Make one. Exactly. Who said math is not creative?
So let's turn tangent squared into tangent.
Right? We can multiply by 1. I believe. Multiply by 1. I know you can do it.
I don't have that much faith.
And then, so tan's an odd power, so let's pull off a sectan. So if we pull off a sectan, we're going to be left with this looking thing. So sectan is going to go hang out over here with dx. Going to mingle with the dx. Right, so all we did was we multiplied by 1. We have to pull off a sectan. Pull off a sectan, we're left with that. That's left over. So the focus here is that we know we're going to let u be secant because the derivative of secant is right there in the pink. So we have to convert those tangents. We need to make those secants also. And tangent squared is secant squared minus 1. And now it's set up perfectly for u sub. We let u be secant, du is sectan, and we are golden. So let u be secant, du will be secant tangent, and this will be u squared minus 1 over u du. And what do we do with that kind of thing? What are we going to do? Split them. If the denominator is one term and the numerator is more than one, distribute. Share, split, split the fraction. Split the fraction. So this will become the integral of u minus 1 over u du. Or you might recognize, last time we talked about improper fractions where the top was heavier in terms of the power. You could do long division, you'll get to that. It's an improper fraction. Long division would give you the same exact thing. That is integrable.
Yeah.
The integral of u is u squared over 2. The integral of 1 over u is natural log of absolute u plus c. And the final step is to back substitute. And we've got that. All right. Powers of secant and tangent. Even power on secant, pull off secant squared. Odd power on tangent, pull off a sectan.
Wait, can you go pick down?
Yeah, I will. 1 second. If we have neither of those options, So if the power on secant is odd and the power on tangent is even, then we're going to convert using the Pythagorean identity. So if neither of those cases work, then just go straight to substituting with the Pythagorean identity. Get rid of all the... So let me just say one more thing about that last one. So if the power on secant is odd and the power on tangent is even, so it doesn't match either criteria, but tangent is even, then you can convert it to secant using the Pythagorean identity, because it's got an even power on the tangent. So you're basically going to convert over to secants. All right, let's take a look at...
Wait.
Yep.
I need to see the final piece.
Oh, that? Natural log of secant. Secant can be negative, so we need those absolute values. Right? Secant is possibly positive or negative, so we need absolute values. Okay, so let's look at that beast right there. So both conditions are met. Secant has an even power, and tangent has an odd power. So let's try to think about which one would be easier. So secant to an even power, we pull off secant squared, and we'd have to convert secant squared over to tangents. Converting secant squared, so just hold that in your mind. Tangent is to an odd power. So we could pull off a sectan, and if we pull off a sectan, how many tangents are left? 8. Converting tangent to the 8th over to secants is harder than converting secant squared over to tangents. Right? Converting tangent to the 8th is going to be more work than converting secant squared. So it's more advantageous. Will you get the same answer? Yes. But it's going to be more advantageous, it's going to be easier if we pull off the smaller, if we pull off just the secant squared, because we're going to have a smaller power to convert. So secant is to an even power. We're going to pull off 2 for the differential, with the understanding that, if we let u be tangent, the derivative of tangent is now presented right over there. So now we have to convert our leftovers. So we have tan to the 9. Leftover secant squared is tan squared plus 1 of theta. We're using thetas now, not x's. So we've got that. Perfect. Perfect. So now if we let u be tangent, du is secant squared of theta d theta. So there is du right there. So we will have u to the 9th times u to the 2 plus 1 times du. Distribute and integrate. We'll have u to the 11 plus u to the 9. We integrate that, we'll get u to the 12 over 12 plus u to the 10 over 10. Tangent to the 10th of theta plus c.
So why did we convert secant to the power? Or do secant squared?
So since the power on secant is even, we're going to pull 2 off, which means there's 2 left over. And then the leftover secants have to be converted over to tangents. So these 2 get converted over to tangents. So anytime we have an even power on secant, we'll pull 2 off and convert whatever is remaining. Does that answer your question?
So we need to go like pull 2 off.
Yes. Yeah, so if secant is even, we pull 2 off. And if tangent is odd, we pull off a tangent and a secant. Pull off one of each. Other questions on that? This just feels so tempting to do something. This feels so tempting. Oh, I have to refrain. So tempting. All right. That is not an even power on secant. So that secant squared is in the denominator. So that's not what we mean by an even power. That even power needs to be in the numerator, so when it pulls off, it's with the dx, or the d theta, or whatever the variable is. So that's not an even power on secant. This is an odd power on tangent. So that's what we're going to do. With an odd power on tangent, we're going to pull off a sec tan. Okay, so let's rewrite this first with positive exponents. Okay, that's an odd power on tangent, so the rule is odd on tangent, pull off a sec tan. Well, once again, there's no secant in the numerator, so what we are going to do is this. We multiply by secant over secant. Now in the numerator, we can pull off a sec tan. So let's see, we pull off our sec tangent, we're going to be left with a tangent squared divided by secant cubed. And then a sec tan is what we are pulling off of to the differential. So when we pull that off, we want to remember that our goal is to let u be whatever function has this as its derivative. So we want to let u be secant, because the derivative of secant is that. So when you're coming back over here, these are the leftovers. That's what we have to convert. With the sines and cosines, it's a little more transparent, because if you put a cosine over here, then everything over here is sine. If you put a sine over there, everything over here is cosine. Here it's a little bit different. You have to be a little more thoughtful. So if we want to have the function on this side be whatever has that as its derivative. So we want these to be secants. Okay, so let's convert those tan squareds. Tan squared is secant squared minus 1. So we're going to have secant squared minus 1 over secant cubed, and then secant tangent. So now we can let u be secant. Let u be secant. Let u be secant, which means du is sec tan. And we once again have a pretty straightforward integral once we simplify. So we will have u squared minus 1 over u cubed du. Is that okay? Seems.
Do you split it?
Now we're splitting it because we have the denominator that's 1. Denominator 1 term, we're going to share it with the numerator. We're going to split it. So that's going to be the integral of 1 over u minus the integral of 1 over u cubed, which in order to integrate, we move it up into the exponent.
Can you explain that part a little more in depth?
Say that once again.
Can you explain that part a little more?
So when the denominator is 1 term, we can split the fraction. We can distribute.
Yeah.
Got it? Okay, that's all right. Good. Yeah, so if the denominator is one term, we can always split the fraction. Split the fraction. Natural log, absolute U. Minus. Add 1 to the exponent and get negative 2. Divide by negative 2, so that's going to be plus 1/2 plus C. Convert back. Is everything okay back there? Chaos strikes.
No, sleep strikes.
Sleeping?
Lack of
Did you
sleep.
fall asleep?
No.
He said you fell asleep.
Lack of sleep.
Lack
I
of
laid down on
sleep.
the desk and I bumped it.
So, do we see that we're going to have a secant squared in the denominator in that middle term?
Yeah.
So what if we want to move the trig function to the numerator? It becomes
Inverse, 1 over.
reciprocal, not inverse.
Well,
That.
cosine.
1 over secant squared is the same thing as cosine squared in the numerator.
Oh yeah.
I just realized secant.
Could you leave it as secant negative 2? No.
You can.
That's what I
We usually don't like negative exponents, so usually you put the secant in the denominator at least. But trying to avoid. I know what you're doing.
Simplifying.
Trying to avoid simplifying. Have no fear. Embrace the simplification.
Yeah, that's it. I just realized, no, I was realizing secant.
All right.
Mirrored.
So, 2
It's
minutes.
a mirror.
Let's take a look at this one.
Secant.
This is the perfect culminating problem. This is not math. This is just pattern recognition. So this will not be on the test.
Thank God.
So if you need, so on the homeworks you may see some higher power. So these are the generalization of the reduction identities. You do not need to know these things. You only need to know how to reduce sine squared and cosine squared. Not this crazy generalization stuff. Even though every semester I seem to have one person that wants to memorize those things. I would not spend my time memorizing those. There are better things to spend your time memorizing. But you should be able to, if you have the reduction identity in front of you, you should be able to follow the steps. So when we look here, the secant is to the 5th power, so the first thing we have to do is reduce it to the 3rd power. So we're just going to, use the n is 5. And then we're going to have 5 minus 2 over 5 minus 1. And then we're going to have secant cubed. So then what do we do now? Do it again. Right? That secants to a cube, so now we just do that again. So we're going to just repeat. I repeat myself. So repeat, so secant cubed, we'll put this 3/4 out in front. Secant cubed becomes subtract 2. We're going to get secant times tangent divided by what?
2.
Divided by 2 plus 3 minus 2 over 3 minus 1. And what's left in here? Secant. All right. So last step, we have that. Let's distribute this 3/4, so we have 3/8 secant tangent plus 3/8 here. All right, integral of secant. I will show you next time how to integrate this. Does anyone know what the integral of secant is? Natural log of secant plus tangent. We'll talk about why next time.
I guess that.
Natural log of secant plus tangent. But again, those big power reduction identities, don't bother memorizing them. if I wanted you to do one on a test, I'd give it to you. On the homework, you'll have it at your, you'll have it. All right, man. See you on Wednesday. Unless it snows again because it's Wednesday. Right?
It's supposed to snow, 80%
Are you serious? You're joking.
I'm not,
Believe. There was like 3 inches of snow last time.
I know we could have skied to school.
We could have. We couldn't even have because there wasn't enough. We were not being like.
Phone says it's supposed to get 4.6 inches.
Oh my gosh! And we have these people upstairs that came from Texas or something.
I have a question.
Mm-hmm.
So,